Okay, so welcome back and welcome all to a new edition of the Quantum Barcelona meetup. Today's edition is all about cryptography, a hot topic these days, and we're gonna explore and describe how quantum impacts as a, let's say, a threat for the classical cryptography, and how scientists are also investigating new algorithms that are quantum safe, and also quantum cryptography and as a new opportunity as well to secure communications in a more, let's say, physical layer. For talking about that, today we bring two experts, Verónica Fernández and Luis Hernández Encinas, two experts on cryptography, both from the Spanish National Research Council, CSIC, in Spanish, who will present the new developments on the two different and at the same time related worlds of cryptography, which are quantum cryptography and post-quantum cryptography. So in order to, first, let me introduce our panelists and especially thank them for accepting this invitation. We have, and Verónica will start first. Verónica Fernández is a tenured scientist at CSIC, where she works in the group of cryptography and information security and in the Institute of Physical and Information Technologies from CSIC. She leads the quantum communication subgroup, where the main research line is experimental quantum key distribution systems in free space transmission channels for high-speed metropolitan applications and related technologies such as beam and polarization tracking systems for atmospheric channels. He has published more than 50 scientific contributions in the field, is the coordinator of the Quantum Technologies Platform from CSIC, an advisory committee of optical satellite communication programs for the European Space Agency, which are also a hot topic these days. Her topics of research include QKD for airborne and satellite communications, discrete and continuous variables, QKD in free space, and novel protocols such as measurement device independent QKD protocols in air. Thank you, Verónica, for being here with us. And let me introduce also Luis Hernández. He's a researcher at the Department of Information and Quantum Technologies at the Institute of Physical Information Technologies on the Spanish National Research Council, CSIC, in Madrid. He obtained his PhD in mathematics at the University of Salamanca in 1992. He participated in more than 40 research projects. He's the author of 11 books, 9 patents, and more than 150 papers, more than 120 contributions to workshops and conferences. And he has delivered more than 50 seminars and lectures and belongs to the several international committees about cryptography and cybersecurity. His current research interests include pre- and post-quantum cryptography and cryptanalysis, pseudo-random number generator, digital signature schemes, authentication and identification protocols, cryptobiometry, side channel attacks, and number theory problems. So as you can see, I mean, they are both really experts on the material and the topic that we're gonna discuss today. So again, thank you both for being here. It is a pleasure. And with all that, Verónica, the floor is all yours.
Thank you so much, Albert, for this nice presentation, introduction. I'm going to share my screen right now. Okay. Can you see my screen now?
Yep.
Okay, great. Well, so thank you again for inviting me to this event. I'm going to talk about quantum cryptography.
Now, you have disconnect the. You need to present again. That we cannot see the presentation anymore.
Oh, okay. Sorry about that. All right. Yes.
Okay.
Press this. Now.
Okay. No. Yeah.
Yes. Sorry about that. So I'm going to talk about quantum cryptography, specifically about the research we've been doing for the last few years here at the Institute of Physical Technologies and Information in Madrid. I would like to thank my research group, which are all these names here, that they have done a tremendous work, and without them it wouldn't have been possible to present this work. So I'm going to give a brief introduction. What is quantum cryptography? Well, it's a set of quantum cryptography primitives. It means that these cryptography primitives are based on quantum principles, such as entanglement and superposition. And for example, private quantum channels is the analog for symmetric encryption algorithms, such as the one-time pad. Quantum digital signatures is authentication, symmetric authentication scheme. Quantum money is for generating and validating banknotes without the possibility of forging. Entity authentication is also used to authenticate users, and with the quantum version of it is quantum proofs, physical and clonable functions, etc., etc. But many of them need quantum memories, for example, and this is not yet available, or they are available but with very short times. So the most widely implemented and the most closer to the application, practical application, is quantum key distribution. So, but why do you need? Why do we really need this? What's the problem with the current solution? Well, many of you know already that there's a quantum computing poses a threat to classical crypto, and this comes from back in the 90s. Wisho's algorithm first proposed, the first quantum algorithm proposed, which reduced the time for factoring large numbers from exponential to polynomial times, and this, of course, virtually breaks public key cryptography. You have a sufficiently large quantum computer. Then you have also Grover's algorithm, also published in the 90s, which reduces the time to search an entry on a database, an assorted database, from linear to square root of the number of entries of this crypto system, which affects, in general, symmetric crypto systems such as advanced encryption standard, for example. Now, this obviously threatens secret key cryptography. And it was previously assumed that increasing the key length, doubling the key length of the algorithm was enough to restore the previous secrecy. But this might not be the case anymore, as the group of Nigel Placentia has proven recently. And they have studied that Simon's algorithm, which is the simplest period funding algorithm, has an exponential speed up from order 2 to the power of n to order n, which some authentication encryption can be completely broken, such as those stated right there. So these threats authenticating encryption too, and it needs to be taken into account. So what can we do in this scenario? Well, there's an alternative solution, or we have the alternative of for providing a high level of security of using, of course, Verna's cipher, which is a very simple algorithm that is mathematically proven to be secure. And what does it need? It needs a key that is as long as the message is used only once and is truly random. So the problem translates into how to generate keys that are completely random and secure. And this is what quantum key distribution can provide. So quantum key distribution is capable of detecting the presence of an eavesdropper in an insecure channel. So this is like, you can visualize this as the eavesdropper leaving a fingerprint of his presence whenever he tries to tap the channel by quantum physics. And this provides information theoretic security to this method. Now, this security means that it's independent of the computing power of an adversary. So even if this adversary has a quantum computer, he won't be capable of breaking the security of this method for key distribution. So this is very important. Also, a nice feature of quantum key distribution is that fresh keys can be generated at any moment, and they're independent from any input state of the system. So this means that if current keys are compromised, they don't have any link to previous or future keys. And this is something that is usually referred to as perfect forward secrecy, and it's a very important feature to have in information security. Now, as I stated before, quantum key distribution is based on quantum mechanics, specifically the famous Heisenberg uncertainty principle, which states that there's certain pairs of variables that cannot be measured unambiguously without introducing an error. And there's also the no cloning theorem, which basically means that you cannot make a perfect copy of an unknown quantum state because basically you would violate the uncertainty principle. You could measure both of these conjugate variables that cannot be measured unambiguously. In this case, you could do it. So there's no possibility of cloning a quantum state. Now, the first QKD protocol was proposed in 1984, the BB84 protocol, and these pairs of variables in this case are non-orthogonal states, non-orthogonal basis states of polarization. So basically, Alice encrypts zeros and ones using these states, these non-orthogonal states, and Bob measures them also with this non-orthogonal basis, and basically, if they share this basis and they keep only the instances in which they use the same basis, then they can share a common key, and they can then check whether there's an error in this sequence, and if it's above a certain threshold that they can determine, they will discard the key because it's not secure. Okay, so it's a method for verifying the security of the transmission, if you wish. Now, there's two main branches in prepare and measure QKD, which is already a branch, but I don't have the time to explain all the protocols. But I will stick to prepare and measure protocols, and within this, there's discrete variables protocols in which the quantum signal is encoded in individual photons and is detected using single photon detectors. And there's the other branch is continuous variables, QKD. And in this case, the quantum signal is encrypted in coherent states, which is basically an electromagnetic field that is attenuated so that there is an uncertainty in the phase space, okay, that is analogous to the polarization, non-orthogonal polarization basis. So this is actually exploited to achieve security, such as in the discrete variable case. And in this case, we can use coherent detectors, which are standard telecom. They use in the standard telecom industry, and they're cheaper. So this option of continuous variables is more closer to the telecom industry, because you don't need to generate or detect single photons. So this is convenient. Now, the transmission channel for quantum key distribution are two main kinds. One is optical fibers, such as in the case of classical communications, and the atmosphere. Now, the problem is with optical fiber is that absorption in fiber will limit the maximum distance you can transmit your link of QKD, because we cannot really amplify the signal in an easy way. You could do it with quantum repeaters, but they're still not commercial. So this still is not an option. And in the case of the atmospheric transmission, the line of sight which you need to transmit in free space is limited by the Earth's curvature. So you have another limit there. So if you want global quantum communications, you necessarily need an intermediate station, such as a satellite, that takes the key from Alice to Bob, which is in another part of the globe. Now, it's worth mentioning that wireless networks are evolving, and they're a more flexible paradigm now, which involves satellites, UAVs, etc., because it's getting cheaper to launch satellites due to the lower size and cost. And this means there's a huge investment in satellite programs that they need to send vast amounts of data from Earth, from climate or defense, etc., that need to be sent back to Earth. And RF links, radio frequency links, are already saturated. So there's this odd option of using optical channels, because they have higher bandwidth. They can support this enormous amount of data that they need to be transmitted. And also the Internet of Things is evolving to many scenarios with lightweight platforms, aerial platforms, autonomous cars, etc., that they need to refresh their session keys. So QKD can be integrated in these wireless networks in a more compatible way than previously thought. So now I'm going to talk about what we've been doing at the SIG. And we started in 2008. And basically, we realized that free space communication, laser communications in urban locations have some use cases that are interesting. For example, they can increase the bandwidth of points that are connected to the network, but they are affected by poor connectivity. So you can lay a free space laser communication link and increase this bandwidth. Also, it's useful to connect local area networks from a same business that has 2 branches and are located in the same city, for example. Also for establishment of connection in case of emergency situations, such as an earthquake, for example, which can damage fiber infrastructure. And the advantages that they have is that it's easy to install. It's not like optical fiber. You need permits, you need to do roadworks, or at the best case, you need to actually lay the fiber, even if you have the installation. So it's also portable, which means that the user moves to a different location. You can relocate your link, and which saves cost and time. And it's also it's got lower cost than RF links because it doesn't need licenses so far, and this is also a good advantage. Now, of course, there are drawbacks. For example, there's some dependence on the weather, especially when there's fog involved, and this would decrease your signal. It would attenuate your signal, and it's also affected by turbulence. So you need some compensation techniques for reducing these effects. So the objectives that for designing a QKD link that would be compatible with this free space situation was the first was to design it at high speed, a fast free space link, and it was capable of operating in realistic conditions, in daylight conditions and in high turbulent regimes. This is because in urban locations there are high turbulent regimes due to the fact that there are many sources of thermal, such as buildings, cars, etc. So we have very high turbulent regimes. Now, so this is the design photo of our transmitter, Alice, which was mounted on a gimbal platform that had 2 motors that provided the elevation and azimuth degrees of freedom with microradian positions sufficient to be aligned with the receiver pole. Now, so this is the diagram of Alice. We use a pulse pattern generator that was capable of going up to gigahertz clock frequencies with very low precision, very low timing jitter of just a few picoseconds. And this generated pseudo-random sequences that could provide control 3 lasers, 2 for the quantum signal at 850 nanometers, and 1 for the synchronization clock. Basically, Alice and Bo had to have the same clock, so we sent this clock through a different wavelength. And the quantum signal was attenuated to very few photons per pulse. Of course, as we cannot have more than 1 photon per pulse because it could be eavesdropped. And it was then launched by collimating packages, polarized, the effects of ellipticity corrected, and it was combined and launched into a beam expander. The beam expander output a beam of about 3.5 centimeters that was sufficient for transmitted at long distances. Now, the receiver bulb used a telescope and to focus the large beams that was received, and a dichroic filter, or basically separated spectrally 2 wavelengths, 850 and 1550. And the synchronization signal went to the clock of a time interval analyzer, basically measuring the time detection events. Now, the 850 nanometers was passed through a very narrow bandpass filter to reduce the amount of solar background radiation. And it was centered, of course, around 850, so to let pass the quantum signal, but subtract all the rest. And then a 1550 non-polarizing beam splitter will separate the 850 into 2 channels, one to receive the ones. And for this, we oriented a polarizer to block the zeros, okay, so that only ones would pass. And the same was done for the channel 0, but to the opposite state. And then we aligned with high precision stages and used optical fiber as a spatial filter and detected with single photon detectors. And this was taken to the time interval analyzer to process the error and to verify whether the transmission was secure, and then process the secret key rate. Also, we introduced some retarded wave plates to correct for electricity induced in linear polarization states, which of course, if it's not corrected, then there's an increase in the error rate. So we found the closest or the only available building that was nearby by the CSIC, the Institute of Agricultural Sciences, and we put our Alice there, and we put our Bob in our institute, and we did a QKD transmission at 1.5 gigahertz, and we proved 2 megabits shifted bit rate and 1 megabit final secure key rate after taking into account several attacks simultaneously. Now, the system is capable of going up to around 2 kilometers in daylight conditions and strong turbulence, but this was the only link that we had available, but we still managed to prove the highest secret key rate at that time in an urban location of a QKD system. Now, when we look at the data, basically we had a 1 megabit secret key rate, but in daylight, there was the solar background at 6:30 in the morning, 7. We had an increase in the solar background that increased our quantum bit error rate and decreased our secure key rate. Okay, and this was because the field of view, what Bob is seeing, the receiver is seeing, needs to be big enough so that we accommodate of the movement of the atmospheric turbulence on our optical beam. But that also meant that solar background photons were also coupled into the detectors. So we realized that, of course, if we could track the beam into a fixed position, we could reduce the solar background without reducing our signal. So we started researching on atmospheric turbulence and its effect on optical beams. And there's basically the beam spreading, which makes the beam enlarge beyond the diffraction limit. That you cannot correct for this, but you can take it into account. Then you have beam wandering, which is random deflections of your beam that they are translated into a kind of random dance at the focal point. And then you have scintillation, which is basically high-order aberrations that deform your beam profile, especially, and also in intensity profile too. So we focus on correcting beam wander because, well, basically, higher-order correction is very, very complicated. It's used in the astronomical telescopes for imaging the universe, like in the Canary Islands, the Grand Telescope. So this is more complex, but beam wandering was something that we could do with this compact optics. So the simplest diagram involves a fast steering mirror, a position sensitive detector, and in a feedback loop that decreases or reduces the error. The error is the error around a fixed position, which you define as the optimal position. So that, if you do it well, it reduces your beam fluctuations. So we researched, we tried different configurations and different detection technologies, and at the end we concluded the optimal configuration, and we mounted the system, which basically involved using 1550 as the tracking signal and synchronization signal, and we used 2 different loops to track the beam in 2 different optical planes that we found as the optimum. And we managed to reduce the beam fluctuations in almost 90%, which meant reducing the error in the system introduced by solar background by the same amount. And this involves an increase in the secret key that we also characterized. And we saw how in this increase in the secret key rate was more than 1 order of magnitude when using a standard telecom fiber, and about 3 times in the case of higher core fibers. Well, now we're also working in continuous variables projects. We're building a system that uses a pilot tone as a reference signal, because we need to use a reference signal to basically send the information to Bob about the phase and the frequency for phase and frequency logging of the signal and the local oscillator. And we're quite advanced there. These systems for free space applications are very interesting because the detection is frequency dependent, so it shouldn't be so vulnerable to solar background light. So this is quite a plus for quantum communications. I must mention that quantum communication is getting a very hot topic in Europe because of the European Quantum Communication Infrastructure. It's an initiative that has been signed by 26 member states. And basically, they have agreed to build this infrastructure that will connect all the large cities in Europe by both fiber infrastructure and satellite and a satellite also connection. And according to the objectives of this infrastructure, we have basically defined our projects too. And the first of it is, as the quantum communication infrastructure has stated, to secure a permanent communication channel between distant buildings and protection of a critical infrastructure. So we are working to connect buildings that are not within quantum communication fiber infrastructure, such as the Telefónica and University Polytechnic of Madrid quantum ring. And so these buildings, they can be connected to this fiber network through a free space QKD link. So we're working with Technobit that will provide the key management, and Polytechnica, who are in charge of this network to do this. And other of our projects is, as the QCI has, quantum communication infrastructure has defined as interfacing space-to-ground platforms and intersatellite connectivity. And for this, we're working in designing a quantum key distribution payload in collaboration with INTA and the Institute of the Canary Islands and other companies such as Alter and Technobit. So very briefly, I will give a final overview of the international powers in quantum communication. Was the state, the first one is the United States, which were first ones to work in quantum communication technologies back in the beginning of the 2000s. And the National Quantum Initiative is an act, was signed by the US President in 2018, and is going to invest more than $1 billion for the next 5 years in quantum technologies. Also, as I just mentioned, Europe is investing strongly in quantum communications. And as you probably heard, China, which is the leader of the quantum communication in the world right now, started in 2007 with the MESIO satellite, and now they have already a fiber quantum network on more than 2,000 kilometers between the main cities, including Beijing and Shanghai. And they have planned more than 10 missions, like Methus. And the final project is to build a global network for 2030. They have already proven an interface free space from their MESIO satellite to this network this year. So I would like to conclude that quantum technologies are strategic and they could influence the geopolitical scenario worldwide. Europe must stay in the leading pack to protect this critical infrastructure and avoid external cyber threats. And member states must develop their own secure infrastructures, which means that each country is responsible to secure themselves. So thank you so much. That's all by me.
Okay, thank you, Verónica. That was very great and a good overview. We started with cryptography, we finalized with even geopolitical issues. So that's great. I mean, communication and cryptography is much more than that, and it's not about only quantum as well. So with that, there's already questions, but I'm gonna take this in the end, because I want to give time for Luis to also give his talk, and then we're gonna jump to the questions. So with saying that, Luis, you can unmute and share your presentation.
Okay, thank you. Okay, I try to oh no, this is not. Wait a minute. It's okay?
We are not seeing, no, not yet.
No, not yet.
Now we see your screen. So then, okay.
It's okay?
Yeah.
Perfect. Okay, perfect. Thank you. Okay. Begin starting, I would like to thank Albert Solana and Quantum Barcelona for the invitation to participate in this meeting about quantum and post-quantum cryptography. And after the presentation by Verónica, I would like to comment some aspects related to post-quantum cryptography, in particular the current state, the current status of this topic. Okay. Well, the contents of my talk are the following. First, a very short introduction, because Verónica said some aspects related to this introduction. The second one will be several proposals, some comments about several proposals we have using today in the field of post-quantum cryptography. And finally, I will comment some aspects related to the standard for post-quantum cryptography and the call made by NIST. Okay. Well, the first question is if we are at the end of the current asymmetric cryptography. It is known that in 1997, Shor published a paper proposing two quantum algorithms that can break in polynomial time if a quantum computer existed some mathematical problems from the number theory, in particular the integer factorization problem and the discrete logarithm problem. These problems are used in modern asymmetric cryptography, and that is if with a current personal computer both problems require an exponential number of bit operation to be broken. With a quantum computer and the Shor algorithms, this time will be reduced to a polynomial time of bit operation, a polynomial amount of bit operation, and a polynomial amount of memory. In relation to the symmetric cryptography, as Verónica said, in 1997, Grover also published an algorithm whereby quantum computing will reduce the time required to break a symmetric cryptosystem to the square root of the current time. That is, a quantum computer will take the same time to do an exhaustive search for 256-bit case as a current PC in a 128-bit key space. If a conventional personal computer needs O of n bit operation to break a symmetric cryptosystem, Grover algorithm and a quantum computer will need O of the square root of n operation and a polynomial amount of memory. Nevertheless, recent publication by Naya, Plasencia, and other colleagues show that symmetric cryptography may not be so prepared to withstand quantum computing. In particular, they have proposed several parallelization of the Simon algorithm. So the first conclusion in this situation is that all cryptosystems and protocols based on integer factorization problem or discrete logarithm problem are vulnerable to quantum computing. In particular, encryption system, key agreement protocol, digital signature, communication protocol, etc. All of them are based on RSA, El-Gamal, elliptic curve, Diffie-Hellman, and so on. So all of them are vulnerable to a quantum computing. Moreover, the security of symmetric cryptosystem will be reduced to half of the current key at least. Okay? So this is the current situation, and then it is important to analyze the relation between mathematical problems and quantum computing. Here we have two sets: the set of math problems on the left, and moreover we have the set of the quantum solvable problems. A part of quantum computing application, we know that the math problems can be divided in two parts. The computationally difficult problems, that is the problem that for to be solved needs exponential or sub-exponential time. And the other part is the computational easy problems, that is the problems that need polynomial time to be solved. But from the Shor paper, we know that the discrete logarithm problem and the integer factorization problem, there are two problems very difficult to solve, now belong to the set of quantum solvable problems. But the point of interest in this situation is that to look at the math problems which are exponential time or sub-exponential time to be solved. In particular, these four problems are very important for the post-quantum cryptography, and the situation is that we don't know if there are quantum algorithms that can solve these four problems. In this way, there are several proposals for post-quantum cryptography. All of them are considered quantum resistant. And these proposals are often based on math problems and implemented in current personal computers. Is code-based cryptography, which is mainly for encryption. And in this case, its security relies on the hardness of decoding error corrected codes. The second one is the hash-based cryptography. It is defined by for signature. And this proposal requires only a secure hash function, secure from a traditional for a quantum point of view. The third case, or the third type of proposal, is multivariate quadratic cryptography. This proposal for encryption and signature. And in this case, the security relies on the hardness of solving system of multivariate equation over finite fields. The fourth proposal is lattice-based cryptography. In this case, it is used for key agreement, encryption, and signature. Lattice-based cryptography relies its security on the hardness of solving problems, solving classic and new problems defined on lattices. And finally, isogeny-based cryptography for key agreement and encryption. And its security relies on the hardness of finding isogenies between elliptic curves over finite field. In the next slides, I will present some specific aspect of each of these proposals, but only a very short comments about each of one. In the case of code-based cryptography, it was proposed by Bakelis in 1978, many time ago. And we know that the error-correcting code theory is a mathematical set of tools that allows detecting and correcting errors that may have occurred when a message is transmitted. This is made by adding redundant information so that the receiver can retrieve the original message. This theory can be applied in cryptography by adding errors to the messages in such a way we obtain a cryptogram, and the cryptogram in this case is the sum of a code word and an error vector with a specific handing weight. In this situation, an adversary will need an extra big time to obtain the code word from the ciphertext, because first he has to determine how to decode the cryptogram. The main implementation of this kind of idea is the Bakelis crypto system in 1978, I have mentioned before. In this case, the Bakelis use as public key a matrix M which define a hidden GOPA code with a specific parameter related to the length of the code and so on. In this case, the plain text is the message. It's a string of a specific number of bits with a specific handing weight. And the ciphertext is computed as the product of two matrices. One of them is the hidden GOPA code, and the other one is the plain text. In this case, for breaking the systems, the attacker must undo the multiplication by M. But the question, the most important question in this case, is that no efficient attacks against GOPA code are known. The advantage of this crypto system is that the ciphertext are short, very short, but the problem, there is a very big problem, that the public key are very large. In here we have an example for a security level of 128 bits with different parameters. And in this case, the public key of this crypto system has around 800 kilobytes. So these are very big in order to, if we compare this length with the normal length used today. The second proposal is hash-based cryptography. This was proposed independently by Lamport and Merkel in 1979. And in this case, to sign a message with 2 to the k bits, we need 2 to the k random string, and this string are considered private keys. Yes. And from this private key, one compute the hashes of these values and obtain partial private keys. And these partial private keys are distributed in as the leaves of a Merkle tree. Then the question now is to compute the public key of the system, and this public key is computed by determining the hashes of each part of connected values in the tree, beginning from the leaves and arriving to the root of the Merkle tree. And the public key of the system in this case is the root of the Merkle tree. There are two signatures proposed in this aspect. One of them is XMSS, and the other one is LMS. In order to see a very short example of how one signature can be verified, in this case, if we can verify the capital S6, we know that the P6 is the partial public key related to this signature, because this signature has been signed with the private key S6. But in order to verify that this signature is correct, we need to know P5, because with P5 and P6 we compute P11 at the hash of the concatenation of these two values. Moreover, we need to know P12, because from P12 and P11 and P12 we compute P14, and moreover we need P13 because we need two values. We can compute P15. If this value, if P15 is the same than the public key of the system, then we can state that the verification of the signature is correct, but in other case the verification is wrong. Well, an example of this kind of signature scheme can be seen in this slide. In this case, the public key and the signature of any message are shorter than in the previous case, so they are very important for the signature in the future. The third proposal is multivariate quadratic cryptography. This was proposed by Patarin in 1996, and the situation we know that the systems of linear equation over finite field are solvable in polynomial time, for example, by using the Gauss elimination method. But we can define a new problem, which is the multivariate quadratic problem over a finite field. In this case, the problem consists in determining a solution to a system of m quadratic polynomial equation that is non-linear polynomial equation in n unknowns. The situation is that we have a set of equation, that we have a system of non-linear equation, and the problem is to solve this system of non-linear equation. It is known that this problem is NP complete, that is, there is no polynomial time algorithms known to solve this problem. The crypto system can be built in a very easy way, because we only need a vector of quadratic polynomial, which is easy to invert. And moreover, we transform this secret key, or this private key, is transformed by means of a true invertible affine transformation, so that this vector polynomial appears random to an adversary. The encryption is very easy, because only has to compute the value of the polynomial vector on the message to be encrypted, and for the grid, the message, the process must be reversed. But for an adversary, if an adversary wants to decrypt a cryptogram, he has to solve a case of the multivariate quadratic problem, which is very difficult for him. But for the legitimate receiver, this problem is very easy, because he knows the original vector quadratic polynomial, and he knows the affine transformation. So for the receiver, the problem is very easy to solve. Example for the same level of security about the number of the length of the public key, but in this case the length is near 4 megabytes, so it's very, very large. But the digital signature is very short, as you can see in this value. The fourth class of proposal are lattice-based cryptography. It was proposed by Ajay in 1996. In this case, the structure that you use is a lattice. A lattice is well known. That is a special subspace, a vectorial subspace, which is given by the integer linear combination of the vector of a base in Rn. And here we can see a very simple example. It's a bidimensional lattice with two bases. One of the bases is good, the red base is good, and the blue base is bad. This reason is because the length of the two vectors, the two red vectors, is more or less the same. The lengths are very similar, and moreover they are near perpendicular, and these properties are not verified with the other two vectors. So for this reason, one is good and the other is bad. Well, in general, when we consider lattice, there are many problems which have been defined in this structure. Perhaps the most important, the most famous vector in lattice is the shortest vector problem. And this problem consists in finding a non-zero vector, x, belonging to the lattice, which is the shortest of the lattice. Similar, well, not similar, it's a related problem with the first one, is the closest vector problem. We consist in giving a vector x in Rn, but this vector x does not belong to the lattice. The problem in this case is to find a vector y in the lattice such that y is the closest vector to the vector original given x. These are classical problems defined in lattices, but in the last year, a new problem has been defined. In fact, this problem, the learning with error problem, was considered by Peckert in 2014 in order to be used in cryptography. This problem is parameterized by an integer n, a prime number q, and a probability distribution g. And one of the versions of this problem is the searching version. And this problem consists of given m independent samples of vectors A and elements by B in Cn to the n and Cq, so that the element is given as the inner product of two vectors plus a error vector. So in this situation, the problem is finding the secret value vector S. This is not a simple problem. It's very difficult and very from a computational point of view. And sometimes some modification or some structure are considered in this problem in order to simplify in some way the operation that we have to do. For example, if the structure is a ring, we have the ring learning with error problem, and if the structure is a module, we have the module learning with error problem. In this situation, there are different crypto systems and different proposals related to different cases: ring, module, or single learning with error problems. And finally, the last class of proposal is the isogeny-based cryptography. This was proposed by Puveine in 2006. In this case, an isogeny between two elliptic curves, E1 and E2, defined both over a finite field, Fq, where Q is the power of a prime. This is I said that an isogeny between this elliptic curve is a group homomorphism, that this is an application between the two elliptic curves that preserves the operation defined in each curve. That is, if we have 2 points and we sum 2 points from the belonging to the first curve, the application transforms the sum of 2 points in the sum of the images of the 2 points given in the first one. Well, two elliptic curves are called isogenous if there is an isogeny between them. But the most important property related to isogenes in the case of cryptography is the following. If we have a subgroup K of an elliptic curve, there exists a unique curve, A modulo K, an isogeny phi, so that the kernel of the application of the isogeny is exactly the subgroup, the given subgroup. This property permits to define a key agreement protocol, which is called supersingular isogeny Diffie-Hellman. It's a key agreement protocol similar to the Diffie-Hellman protocol. In this case, the two users, Alice and Bob, using an elliptic curve and defined by a set of public parameters. And from then, each of the users define an isogeny, which is secret for each user. And later, they share several parameters in order to obtain a second isogeny related with the first one. But at the end of the process, both users obtain the same elliptic curve, and from this elliptic curve, they can define or they can choose some invariant of the elliptic curve, for example, the J invariant of the elliptic curve, in order to use this invariant as the seed for generating a key which be shared by the two users. The secret part of the protocol depends on the kernel of the two isogenes, and it is important to mention that only supersingular curves can be used, because for non-supersingular curves the protocol has been broken. In this part, I finished the second part of my talk, because I have presented the most important protocols or proposal based on mathematical problems which are considered too difficult to solve today. But in the third part, I present only two slides related to the process to find post-quantum cryptography standard. The NIST calls for future quantum resistant standards only affect to asymmetric cryptosystem or key encapsulation mechanisms and digital signature. This call has specific constraints related to security, cost and performance, and implementation. Here you can see the schedule of this call. As you can see, the call starts at 2016, and it is possible that in perhaps 2 or 3 years we have a publication of the first draft standard, and this is our hope. But originally, 69 algorithms were accepted in the first round in 2017, sorry, and 26 algorithms progressed to the second round in January of 2019. Now we are in the third round, because in July of the last year, 2 lists of algorithms were published. The first list is a set of finalists. This is composed by 4 cryptosystem and key and 3 digital signatures, and you can see here the names of these finalists, and you can see that most of them depends on lattice problems and multivariate quadratic problems and GOPA code, which is the McEllis that we have mentioned. And moreover, an alternative list of 5 cryptosystem key and 3 digital signature has been published in order to substitute any of them if some of the previous will be broken, possible will be broken. But it's important to mention that this is the situation in this moment. All of these protocols and algorithms are under study, and in 2 or 3 years we can obtain the final draft of the different protocols to be applied and to be considered as a standard. And finally, I'll present a couple of slides with some references. If you are interested in this topic, you can consult. You can see these references. Okay, thank you, and many thanks for your attention.
Okay, thank you, Luis, for your presentation. Now I feel much more safe, that where I know that there's many algorithms that are quantum safe. So it's not always about RSA, but it's also on new research that is going on. And actually, there's a questions about that I'm gonna bring, and then we're gonna jump with other questions for Verónica. But the Jaime is asking, is any of the post-quantum crypto families believed to be more interactable by quantum computing than others? So from the ones you presented, is there some of them that, let's say, quantum computers feel like more a challenge, or not? That's...
So the question is for Verónica, I suppose.
No, it's for you. It's just from the in terms of post-quantum cryptography algorithms, is there some of them that feel more a challenge than the other ones?
Well, you are asking what is the best, the best of them, more or less. It is difficult to state, because I think that NIST, the goal of NIST is to choose one of each kind of proposal. That is, at the end of the process, at the end of the call, NIST will select one for codes, one based on code, one based on hash, one based on multivariate system of multivariate polynomials, and one for lattices. It's not clear if for isogeny will be selected any of them, because the isogeny only belong to the alternative, not to the finalist. So the last decision is by NIST, but one can use one of them if you prefer to use one of them. But if you want to use an standard, international standard, you will be obliged to choose one of them. But if you are a private company, you can choose any of them if you are convinced that they are secure. They are no broken, no has to be broken.
Okay, good to know. And so jumping on questions about Verónica, so there's a few, and we have just 5 minutes to go, but there's a couple. First, about like the communication. So for instance, Manu is asking that you said that there are using repeaters and they should be possible. So in a sense, yeah, this is equivalent to make a copy. So does it violate the Heisenberg principle?
That's a very interesting question, and I have to congratulate the person that asked it, because it makes sense after what I said. So I'm just gonna share my screen to explain it a little bit more visually. Right. So basically, quantum repeaters, what they do is when you have a source of entangled photons like this, and then you have another source of entangled photons here, then you can make a measurement here which basically reproduces the entanglement between now this particle here and this other particle here. So if you do this indefinitely, just doing many sources of entanglement pairs, you would, in principle, theoretically, extend this distance indefinitely. So it's not based on copying; it's based on extending or distributing this entanglement over particles. Okay. So it's based on a completely different principle. It's not really copying. It's based on entanglement.
We would say that here we just have used the language saying a copy, just that everyone understands that, but it's a key of entanglement.
Yes. Yes.
Okay.
Entanglement here. Yes.
Okay, great. Thanks. Let's go for another question from Ricardo. Also, in terms of communications, he's asking how do you distinguish between an eavesdropper taping the quantum key
Yes, well,
channel?
Very good question too.
And the noise free. Yeah.
You cannot distinguish the noise introduced by an eavesdropper or by any other source of noise in the channel or in your receiver. But what you do is you characterize the noise before of your channel and of your receiver, everything. You characterize that noise, and then on top of that, if you have an eavesdropper, it will add to this noise. But at the end, there is a threshold in which you wouldn't have any kind of secret key now. So it doesn't. It's relevant that you characterize your noise, but at the end of the day, it will add up to an eavesdropper. So you cannot really differentiate it. You characterize it, but at the end, it's included in your calculation, and it would really reduce your secret key rate, even if you know it's your own source of noise, your receivers or your channel, but it still is limiting. It's already reducing your secret key rate, because the higher you have the error, the lower is your secret key rate. I don't know if I explain myself.
Mm-hmm. Okay, yeah. Just another question from you, and then I'm gonna check if there's also more questions from the post-quantum. So one question more like experimental, because Akash is asking how how he can demonstrate all the QKD in a let's say in an undergraduate lab and like in a small level.
Yeah, this is a simple setup of the simplest protocol for QKD. So you need to generate two non-orthogonal states here and here. So they have to be at 45 degrees. So you need to attenuate them so that you have only one photon per pulse. You combine them. You need a clock. So you need to send the clock. And then it's basically it's the simplest version of what I explained before, but the clock needs to go to your electronic card, and then the two states are detected by setting your polarizers against the state you want to block. So this is the simplest way to do it in a lab. You get rid of the transmitter telescopes because you won't need this in a lab. You need in a short distance. But you need non-orthogonal states. You need single photons attenuated in your lasers, and you need single photon detectors and an electronic card to detect the detection events. So this is the simplest way to do it.
Okay, just one question for Luis, and then we need to wrap up because it's already 7. Just continuing about what you were saying. You were saying that we can wait for NIST as the as the final candidate as the best one. But let's say NIST is from the United States. What algorithms or what research are doing here in Europe? Are here providing any standard in that sense?
Okay, there are no initiatives from Europe. Okay, so we are waiting for the final decision of NIST because this is the most important situation. There was several proposals by different universities, but their proposal or they call was very restricted. So in Europe, we are waiting to the final decision by NIST in order to consider what is the best set of proposal to be used as a standard. But from the point of view of Europe, there are any proposal, no proposal, any initiative in order to obtain the final decision. In any case, it is important to mention that each country can decide what is the most important decision or most important proposal or more convenient proposal for the country. For example, it is known that the national organism from Germany, they prefer, for example, Frodoken, but Frodoken from NIST is considered as an alternative, not a finalist. So the final decision depends on the country, or the government of different countries and so on. But all people is waiting for the final decision by NIST.
Okay, I mean, yeah, it's good to know, as you just already mentioned, that it is good that even the final candidates, they are well enough in order to be adopted for any country. So that's also like a good initiative. So each country can decide by itself.
Yeah, it's a similar situation that the other standards like SHA-3 and AES, for example, this is the same situation. Remember that the proposal for string cipher, eStream, this was a European proposal, but the most important decision is the NIST decision, I am afraid.
Yeah. Okay. So with that, and I know that there's many other questions, but I mean time is up, and we try to answer them. But thank you both for attending this new quantum meetup about cryptography. Thank you all for attendance this meetup, and just wait for another event next month. And let's keep in touch and continue at least virtually. Thank you very much, all.
Thank you so much, Albert.
Thank you so much to you. Thank you very much.
Time. Bye.
Okay, bye.